We see 5 velocity time graphs up on the board right now. Each of them have velocity on the y-axis and time on the x-axis. That means that for each of them, which one is the manipulated variable? Time, right? Time, or the x-axis is always the manipulated variable, and you can see that it always goes second in the title as well. We saw position time graphs of the exact same shape a couple weeks ago. What I want to do today is spend just a couple of minutes reviewing those position time graph shapes and then relating them to these new velocity time graph shapes. So what you see written in blue in just a moment will represent what this this graph would be if it was a position time graph, and when you see written in red underneath it will be what the velocity time graph represents. All right? So tell me, if that first graph was a position time graph, what would it represent? What would it mean? You got a straight line, right? We saw an activity here last week that you guys headed in, I think on Friday, got back yesterday, that had a straight line on a position time graph. Maddie? Yeah, it would represent constant velocity. Now, remember that we put a little star there to remind you that that's not what we've got here. If it was a position time graph, it would be constant velocity. What about the next one? If it was a position time graph. In blue, I'm going to write what? Yep. Yeah, it's not moving. Now, clearly, in this case, when it's velocity time graph, it is moving. But if it was a position time graph, it would be stopped. It would be at rest. It would be not moving. What about the third one? Position time with a straight line once again, but this time sloping downwards. We would say this is no, we wouldn't say it's a deceleration if it's a position time graph. Yeah. Yeah, it's a constant velocity because it's a straight line, but it's in the negative direction because the slope ends up being a negative value. Let's say constant negative velocity. And the fourth one, position time. This represents acceleration, right? We saw this last week where an object is speeding up. The position is changing, but it keeps changing by more and more and more as time goes by. And the last one represents, we can call it a couple of different things, bless you. Deceleration, negative acceleration, whatever you want to call it, if it was position time. Now, in red underneath, I'm going to write down what it represents for the velocity time graph as we really have here. If this velocity time graph has a straight line sloping upwards, what do you think it represents? I'll give you a little hint. Go back to your activity that you did yesterday. Found the slope of that, right? That velocity time graph. Yeah, this is what we call constant acceleration, or usually in the context of acceleration, we call it uniform acceleration. But it means exactly the same thing as constant. So constant acceleration, uniform acceleration, constant velocity, uniform velocity, whatever. Just that we usually see the word constant with velocity and uniform with acceleration for some reason. Next one. This one stopped? No, it's not. Look, there's a velocity. There's a velocity. So what's going on here? It's a constant speed or a constant velocity. Notice we're using the word constant again, although it doesn't really matter. Constant, uniform, whatever you want. Constant negative velocity? No, the velocity is changing here, right? So how would we describe it if the velocity is changing and the velocity is decreasing as time goes on? Right? Yeah, we would say this is a constant deceleration or constant negative acceleration or a uniform negative acceleration. Any of those things would work. Next one. This could be a bit tricky. We want to be as specific as we can with this as well. Is the object speeding up? Yes. Jen, is the rate at which the object speeds up staying the same? No. So not only is the velocity increasing, but the acceleration is increasing here as well. If this was If we look at graph number 1 over here, this would represent putting your foot on the gas pedal of your car, accelerating, speeding up at a normal uniform rate, keeping your foot on the gas pedal in the same place. The fourth graph would represent you putting your foot on the gas pedal just a little bit, speeding up, but then as time goes by, you keep putting your foot further and further and further down on the gas pedal, so that not only does your speed increases, but the rate at which your speed increases. Is that okay? So your speed is increasing, but so is your acceleration. Whereas in graph number 1, it's just your acceleration stays the same, your speed continues to increase as a result of that acceleration. So we're going to say here that this is increasing acceleration. Now, what about the last one? That's slowing down, deceleration. Look at the graph. Look at the graph near the beginning, and look what the velocity is. Look at the graph near the end. The velocity is higher. Is it speeding up? Yes, it is. But it's not speeding up as quickly as it was at the beginning. So the rate at which the velocity increases, fill in the blank. The rate at which the velocity increases decreases. It's like putting your foot on the gas pedal right down to the floor, but then you kind of ease off. You continue to speed up, but as 5 seconds after you started, you're not speeding up as quickly as you were when you started, but you're still speeding up. So your acceleration is decreasing, but your velocity is still increasing. We're going to say decreasing acceleration, but don't get that mixed up with slowing down. We're still speeding up. We're just not speeding up as quickly as we were before. Now, you see that there's 10 different graphs that we've looked at, shapes and so on. Don't memorize those, right? Like, think about each and every one of them. I know sometimes that takes a little bit more time to solve a problem when you're thinking about it versus memorizing it. But I don't know about you, but when you start putting all this stuff in your head, think like, man, there's so much to remember. How am I going to possibly remember all this? Exactly. You probably won't remember all this. So don't memorize things you don't have to memorize. You figure things out if you can figure them out, and memorize only the things that you absolutely need to. Okay, I want to take a look at how we're going to analyze each of these graphs now. Let's say we've got a velocity time graph up here. Time on the x-axis because it's the manipulated variable. Let's say we've got a line that looks like this, 2 lines actually. Tell me what's happening in phase 1. Yep. Good. We're accelerating. We're speeding up. It's a uniform acceleration in phase 1. And in phase 2, it's, yep. Yeah, constant velocity, right? It's not speeding up, slowing down. It's still moving, but it's not speeding up or slowing down. All right, we want to find the instantaneous velocity on a velocity time graph. 3 words. What do you think they're going to be? Easy 3 words. Rachel? Up and over. Up and over. So if you want to find the instantaneous velocity at this time, go up and over, read the velocity. At this time, go up and over, read the velocity. Up and over. Listen, if you want to find the position on a position time graph, up and over. The velocity on a velocity time graph, up and over. The force on a force time graph, up and over. The momentum on a momentum time graph, up and over. The whatever on a whatever time graph, go up and over. Now the change in velocity, you can imagine here would be like start finding the displacement on a position time graph. Go up and over to get the velocity, go up and over again to get the final velocity, and subtract the 2. Really what we're doing here is saying delta V is equal to VF minus VI. Finding the acceleration on the velocity time graph. If you look at individual sections, you can find the slope, or you could just say A is equal to delta V over delta T, which really boils down to the same thing as the slope. Delta V is the rise, delta T is the run. As long as you have only one thing happening, you're not sloping upwards and then changing, right? If you're looking at just one section of time or one section of the graph, you can use delta V over delta T, or the slope works fine. And finally, the displacement. This is the hard one. Although you might have done it in Science 10. The displacement on a position time graph. Yep. Good. It's the area. But be careful with the way you said that, the area underneath the line. Sometimes you have a graph that looks like this. And it is the area. Say, there's my graph. It is the area. But it's not just the area beneath the line. Okay, when I've got a graph that looks like this, it's also the area above the line. So it's the area between the line and the x-axis. Does that make sense, Charlie? The area between the line and the x-axis. This red would represent a positive area if I was to calculate that. And this blue would represent a negative area if I was to calculate that. And then we just combine it, add them up. If the total worked out to be positive, then my displacement would be a positive value. If the total worked out to be negative, my displacement would be a negative value. Now, of course, a lot of times there's not just one simple shape that we can find the area of. We have to break it up into sections. You're going to see that happen in just a moment when we do our first example. First example is on the front of the page that I handed out a few minutes ago. It's this one. We got a velocity versus time graph. Velocity on the y-axis, time on the x-axis. We're going to find the velocity at 4 seconds. So what do? We go up and over at 4 seconds. Up and over, looks like 15 meters per second. Easy enough, right? The change in velocity of the entire graph. Well, that's going to be final minus initial. The final velocity is, it's kind of hard to tell on this one. I promise you on a quiz or a test, you're going to have more grid lines, so it's easier to tell exactly what the number is. What does it look like, though, the final velocity? Oh, 33? Yeah, that's what it was supposed to be. The initial velocity, Braden? Yeah, it's supposed to be 3, but if you said 4, when it looked like this, I wouldn't zing you for that, because it's pretty hard to tell exactly what it is, right? Again, on a quiz or a test, it would be clearer, more clear to you. That gives me a total displacement of 30 meters. Now, the acceleration over the entire graph, take the slope of that, which is rise over run, but the rise corresponds to delta V. The rise is 30 meters. The run is 10 seconds. The acceleration is 3.0 meters per second squared. And the displacement. What do I have to watch out for here for the displacement? What is it that's going to lead a bunch of people to a mistake here? What kind of shape do we have here? Was your hand going up there? Pardon me? It doesn't start at 0. Yeah. And because it doesn't start at 0, we actually have 2 shapes, right? We have a rectangle and we have a triangle. We got to find the area of both of those. The area of the rectangle is base times height, or you could say length times width. The base here is 10 seconds. The height here is 3.0 meters per second. And you'll notice here that the seconds end up canceling, one on the top, one on the bottom, and we're left with 10 times 3 is 30 meters. Then we got to find the area of the triangle, which is 1/2 base times height. 1/2 of base, which is 10, and the height is, oh, can we get this one? 30, good, not 33, because the triangle isn't 33 high. The height goes from 3 to 33, so the height would be 30. We're going to say 1/2 of 10 times 30, which is 150. And then we go to add those up. Because they're both above the x-axis, they're both positive. Add them up, we get 180 meters. So there you go. My instantaneous velocity, my change in velocity, my acceleration, and finally my displacement. Quick little question that I didn't ask here. What if I wanted to find the average velocity over the entire trip? The average velocity over the entire trip. What would I do? The average velocity, despite the fact that there's an acceleration here, would be displacement divided by time. It's a group B problem, really, because it's acceleration. But if we're looking for the average, then we go back to our average constant velocity question. My displacement is 180 meters. My time is 10 seconds. My average velocity would be 18 meters per second. Question. Okay? All right, I want you to work on the questions on the back of that sheet now. It's 1 to 4 on your velocity time worksheet. All right, taking a look at number 1, it says, what's the velocity at t is equal to 6 seconds? At 6 seconds, you're going to go up and over. We do that. Appears to be about 5.0 meters per second. Okay, easy enough. Second one, the change in velocity between 0 and 9 seconds. We're going to do the final velocity minus the initial velocity. VF minus VI. VF is, what, 5 meters per second? And VI would be, no, it's not. It's, VF is what? In 9 seconds, it appears to be up and over 7 meters per second, and VI is 1 meter per second. So we're going to say that's 6 meters per second. Acceleration, because it's one straight line, I can find the slope of it, but I usually do this. A is equal to delta V over delta T, which is fine because it's exactly the same thing. Delta V is the rise, and I know that that's 6 meters per second. Delta T is the run, and that's 9. So that's going to give me 0.667 meters per second squared for the acceleration. And finally, the displacement. To find the displacement, I have to break it into 2 sections because I have a rectangle down here and I have a triangle up here. I have to account for that rectangle. I'll tell you, one of the common mistakes that we see here is that people find the area of that triangle and don't find the area of the rectangle. They forget to do that. We have to include that. So the area of the the rectangle is section 1. We're going to say it's base times height, which is 9 seconds times 1, which is 9 meters. And then we're going to say the area of the second section is 1/2 base times height, which is 1/2 of 9 seconds times the height, which is, what is the height of that triangle? What is it? Yes, 6. So we're going to say 1/2 of 9 times 6 is going to give you 27. And then what are we going to do? We got to add them up, right? 9 plus 27 is 36 meters. Good. Now, just as a little aside here, it's entirely possible nobody thought of this, but let's just take a look at this, okay? What if we had said, what if we use this equation, d is equal to VIT plus 1/2 AT squared? What is VI there? 1? What's the time? No. What's the time interval for this whole thing? 9. What's the acceleration? 0.667. And the time is 9. Let's figure this out. let's say 1 times 9, add that to bracket 0.5 times 0.666667 times 9 squared. Oops. And what do we get? 36. 36 meters. Go figure. Okay, if we do it mathematically like we've learned to do word problems, then we get 36 meters. If we do it graphically, we get 36 meters. Does that show you that the area represents the displacement? Does that show you why you have to include this, which a lot of people tend to forget? Okay. All right. Keep going. We'll go over to question number 2 in a little bit, but we're going to give you a little bit more chance to work here before we do that. Okay, we'll do one more of these questions. Take a look at number 4 here now on the sheet. It says, what's the acceleration between 0 and 25 seconds? And what's the acceleration between 25 and 45? Acceleration, we know is, we could find the slope of that line, or we can just say delta V over delta T. Delta V is what? 80 minus 0. That's the change in velocity for that phase, that first phase, 0 to 25 seconds. And the time interval was 25 seconds. So we're going to say 80 divided by 25 would be 3.2 meters per second squared. And the acceleration in the second stage, we're going to find the same way. We're going to get a different number here. What would you expect to get here? Positive or negative value? Negative. Would you expect the value to be bigger or smaller than we got in the first one? Good. Bigger, because your velocity is changing by the same amount, but yet it does it over less time. So we would expect to get a value that's probably not a great deal bigger, but still bigger, right? So let's find delta V here now. We're going from, what, 80 meters per second down to 0, so we're going to say 0 minus 80, divided by my time interval, which is 20 seconds, from 25 to 45, 20 seconds. So what do we get? Negative 80 divided by 20 gives me negative 4.0, and that's going to be meters per second squared. Negative tells us that we're slowing down, and 4, we predicted that it would be a value that was a little bit bigger, and sure enough, it was. We didn't have to find the area of this because we weren't looking for the displacement, but what if we were? We got to break this up into 2 triangles? No. If you're using trigonometry, you got to break it into triangles that are right angles. But for this, for 1/2 base times height, you can just say 1/2 of 45 times the height of 80, which is, what is that? 1/2 of 80 is 40. 40 times 40 is 1600. 5 times 40 is it 1800? Just check that, but I think it's 1800. Would be my displacement if I was looking for my displacement. Okay?